Okay, thanks a lot for your kind introduction. Thanks a lot for the invitation. It's great to be here in Jerusalem. It's my first day ever in Jerusalem and first visit to Israel. So thanks a lot for the kind invitation. And it's not only me, because you get both of us. You also get my doctoral student, Joseph Chege, who will give the second part of the talk. So we'll have everything for you today. If you have a question, please feel free to ask. You've already mentioned the title, Efficient Maximum Likelihood Estimation of a Low-Rank Probability Mass Tensor from Partial Observations. And this was actually joint work with Aryeh Yeridor from Tel Aviv University. So please raise your hand if you heard the name before, Aryeh Yeridor. Okay, some students have heard, yeah. So we just visited him because we have a joint project on this topic, actually. So we're just talking about this topic. This is a picture from our campus. So Ami should know the campus. He has been there. So it's in the mountains, basically. And this is another picture from the campus that gives you the outline of the talk. So,
Tel Aviv University.
Pardon?
It really reminds me.
No, it's not Tel Aviv. It's Ilmenau. So it's not Tel Aviv University. It's much smaller than Ilmenau, and you can see the mountains from campus. This is actually the main lecture hall here that seats about more than 600 people. And if you sit there, you see the mountains. Okay, and we also have concerts there, symphony concerts and jazz concerts. And yeah, so but today we want to talk about PMF estimation. So first of all, let's look at the motivation for estimating the joint probability mass function tensor of a set of random variables. Then we look at modeling of the naive Bayes model via the so-called canonical polyadic tensor decomposition, CPD. And then we want to distinguish different methods of estimating the joint PMF's tensor. The first one is based where we on third order marginals. So first we estimate third order marginals either using least squares criterion. This was the original publication. Then we propose to use the Kullbach-Leibler divergence criterion instead. And in the second case, we don't first estimate these third order marginals, but directly use the data. And there we also propose two different methods, one based on alternating directions minimization and one on EM. And I saw you already covered EM in the minutes before, so that's good. Expectation maximization. Then Joseph will talk about some simulation results. First, synthetic data experiments where we know the ground truth. And he will also say a few words about how we can speed up the convergence of the EM algorithm and introduce SQUAREM. And then we also talk about some real data experiments where we use movie recommendations, movie evaluations. And then finally, we will conclude. So let's look at the motivation first. Estimating the probability mass function from partial observations of a discrete random vector, of course, is a core problem in statistical learning, as you all know, since the knowledge of the joint PMF is considered as the gold standard. So, because it enables optimal estimation under various criteria, such as, for example, the mean squared error criterion and the minimum probability of error criterion. Useful applications, once you have the PMF, include recommender systems, for example, for the recommendation of restaurants, hotels, and movies. We talk about movies later on. By using the joint PMF of ratings, we can predict, for example, missing ratings based on the conditional expectation of the available ratings, and we'll look at this problem in the sequel, and then can make recommendations based on these predictions. So we can recommend certain movies, certain restaurants, certain hotels. And another problem would be data classification, where we use the joint PMF of the features and the label to infer the label from a test sample according to the maximum a posteriori principle. For example, if we look at biomedical signal processing, the label could be whether a person has a certain disease or not, and then the random variables could be certain symptoms. And then we could try to infer the label whether the person has that disease according to the maximum a posteriori principle after estimating the joint PMF tensor. Okay, usually the full PMF, of course, is unknown, and we want to estimate it from the data during a training stage. So estimating the joint PMF via histograms, so this would be the straightforward approach, of course, is considered virtually impossible due to the curse of dimensionality. For example, because the required amount of data samples grows exponentially with the number of variables. For example, if we have 10 variables, 10 random variables, with 10 distinct values each, we would have to estimate 10 to the power of 10 parameters. And histogram estimation also is very inaccurate since we have a very low probability of encountering any particular realization of these 10 to the power of 10 possibilities, of course. A lot of data is required to obtain a reliable estimate, and even more in the case of incomplete data. Incomplete data because not everybody has rated every movie, right? So let's consider a set of capital N random variables, xn, and each variable xn takes in discrete values. So our aim now is to estimate the joint PMF, that is the probability of x1 through xn x capital N from partial realizations of these capital N random variables. So how would we then, let's assume we have the PMF, how would we use this joint PMF for data classification, for example, okay? Given a set of features, let's say x1 through x capital N minus 1, so x capital N is missing, we want to compute the posterior probability and predict the label x, and this could be the label whether this person has that certain disease, using the maximum a posteriori principle. So this would be the probability of xn being equal to in given the values of the other capital N minus 1 random variables. So this is, of course, the joint probability of all n random variables divided by the joint probability of the known capital N minus 1 random variables, and we get that one by marginalization. So we just sum over all possible values of in from 1 to capital In. Okay, and in a recommender system, given a subset of ratings, x1 through xn minus 1, we want to estimate xn using the conditional expectation. So that's the conditional expected value of xn given the other n minus 1 random variables. So we just sum over all possibilities of in and weight the corresponding conditional probability of xn being equal to in given the other ratings. And of course, this conditional probability is computed according to equation 1. If there are any questions, just let me know. But these are basics, I guess. Let's look at a toy example. This is so let's consider 4 movies with 5 possible ratings. So movie 1, I'm not sure whether you know these movies. Movie 1 would be Toy Story, movie 2 Shrek, then Inception and The Batman. So the joint PMF of a user's rating can be represented in this case as a 5 by 5 by 5 by 5 tensor X. So for example, this entry here, X of 1, 3, 4, 5, would be the probability that the user rated Toy Story as 1, so he doesn't like Toy Story, Shrek as 3, Inception as 4, and he likes the Batman as 5. Suppose this user has rated Toy Story, Inception, and the Batman, but has not watched Shrek. So if we know the joint PMF tensor, we can easily predict the user's rating for Shrek. How can we do that? We calculate the posterior probability vector R, which is 5-dimensional because there are 5 possible values for the rating of Shrek, right? So the ith entry, this would be R of I, is the probability that x2 is equal to I given the other 3 ratings. And of course, this is the same formula that we had before. So we marginalize here the joint PMF for the second random variable. Then we can calculate the MMSE estimate of the rating for Shrek using the second formula from the slide before by just weighting the corresponding posterior probability vector by the corresponding value of I. And then, based on the estimated rating, we can decide whether or not to recommend Shrek to this particular user. Okay, this was the example. Now let's look at modeling of the naive Bayes model via the CPD. And the joint PMF of the random variables x1 through xn can be represented as an n-way tensor. So this would be of size I1 through by I2 up to In. And each element of x is then the probability of a particular realization, that is, of a particular index combination. For example, this entry here would be the probability that x1 is equal to I1, x2 equal to I2, up to xn being equal to In. And then X actually admits a rank R canonical polyadic tensor decomposition. What's that? So we have the sum over capital R rank 1 tensors that are basically the outer product of the rth column of all n factor matrices an weighted by the rth component of the loading vector lambda. And we want to use this familiar shorthand notation for the n-way CPD. So this is the weight vector lambda and the factor matrices A1 through AN. So the loading vector and the factor matrices, and this denotes the outer product. Okay. So, questions? No.
This is an assumption, the rank R.
Yes, sure. Yeah, exactly. Yes. But we can find the corresponding rank. And we also have some techniques, and Joseph can talk about the techniques later on in the discussion session part. So the probability, and Joseph can also talk about how we found the rank, for example, for this movie length database. Right. So the probability of a particular, yes.
So does it correspond to a mixture of our product distributions, or is it?
So in this case, it's just a CPD. We're not talking about the base. We're talking about the equivalence between the CPD and base model in a second. Okay, I've just introduced the CPD, that it's basically a rank R tensor here in this case, that you can write as the sum of R rank 1 tensors. Right? And the rank of a tensor can be larger than, so this is like in the matrix case, but unlike in the matrix case, the rank of a tensor can be larger than the smallest dimension. Okay. So the probability of a particular index combination is given by this corresponding entry of the tensor. Again, this is the formula from the previous slide. And of course, we can write this product also with this shorthand notation. And this is again a picture, right? So here we see the, for n equals 3, this is a 3-dimensional tensor. We see the corresponding weighting of these rank 1 tensors with the corresponding values of this loading vector, lambda 1, lambda 2, up to lambda r. Just a picture of it. So now let's look at the naive Bayes model. So in practice, there's also this naive Bayes model because in practice, the random variables usually have some degree of dependence. That means they're not fully independent or fully dependent. If they were fully independent, the tensor would have rank 1. So a reasonable assumption is that the random variables are independent given another hidden or latent random variable, let's call it h, that takes a finite set of capital R values. So this is known as the naive Bayes model, and that means that our random variables x1 through xn are independent given the latent variable h. So let's form this mathematically as well. So the probability of a particular realization according to this model is then given by this formula. So here we basically also sum over the capital R possibilities for our hidden random variable. That's the probability that h takes the value r. And then they're conditionally independent, so we can just take the product of the conditional probabilities here of x1 being equal to I1, given, of course, that h is equal to r, etc. Right? And obviously, this is the shorthand notation with the product. And we see the similarity, right, between the CPD and the naive Bayes model. Here again, the picture of both. And obviously, the a priori probability of our latent random variable h corresponds to the elements of the loading vector. And then the conditional a posteriori probability, here the probability of xn being equal to in given this latent random variable h being equal to r, corresponds to the corresponding entry of our factor matrices, entries of the columns of an actually. And so note that the elements of the loading vector are positive and they sum up to 1, and the elements of the factor matrices are non-negative, and the columns also sum up to 1. And these are the probability simplex constraints that we have to fulfill for our CPD. So X admits a non-negative CPD with these special probability simplex constraints. So you see that the naive Bayes model leads to a nice Bayesian interpretation of the CPD. And let's consider again our earlier example with the movies, Toy Story, Shrek, Inception, and The Batman, with 5 possible ratings. If there are 2 kinds of users, let's assume we have action lovers and animation lovers, then we may have that 40% of the users love action movies and 60% animation movies. Right, so these are the a priori probabilities of the different populations, and this could be the factor matrices, right? So, so the columns of the factor matrices actually provide the probabilities of the ratings 1 through 5 for the different populations. So this is for the action lover movies, and this would be for the animation lover movies. And the animation lovers, of course, rate the animation movies higher, like Toy Story and Shrek. Toy Story, yes, and Shrek, they're animation movies, so they have a higher rating for the blue populations. And Inception and The Batman, they're action movies, and of course they get a better rating for the action lovers population. Okay, the implication is that any joint PMF admits a naive Bayes representation with a finite latent alphabet, and this was shown by Nikos Sideropoulos and his co-authors in this reference 1. The number of states R that the latent variable H can take is bounded, of course, by the rank of the tensor. And this is a very loose bound here. Uniqueness, however, is not guaranteed. In addition, the CPD uniqueness conditions have to be fulfilled to guarantee uniqueness of our CPD. So let's look at the PMF estimation next. And there are 2 main approaches for the estimation of the PMF tensor. One is marginal Bayes, where we first compute third-order marginals, lower-order marginals in general, and then fit them to the CPD. And this was done in this original reference 1 and in our USIPCO paper 2. And the second approach would be data-based. We're also going to talk about that, where we find actually the maximum likelihood estimate of the joint PMF using directly the observed data as published in 3. So let's look at the marginal-based estimation approach first. And the full joint PMF can actually be recovered from marginals of order greater or equal than 3 under relatively mild conditions as shown in 1. The idea is that it's easier to obtain a reliable estimate, empirical estimate of lower order marginals than of the nth order probability tensor. And the lower order marginal distributions also admit a non-negative CPD, as we see next. So this would be the joint probability of n-1 random variables where this ik is missing. So we just can sum over all possible values of ik from 1 to capital Ik. And now we express this probability via the CPD, as we can see here. And we can actually eliminate the dependence on the factor matrix AK by just summing over all possible values of Ik here, right? So, the columns sum up to 1, so we just, due to the probability simplex constraints, and now we have eliminated it, and we get a non-negative joint CPD of the remaining n-1 variables. So the order of the tensor has been reduced by 1, and we can continue this process until there are only 3 variables left, and then we get a third-order tensor. Okay, and we estimate the third-order marginal PMF empirically, that is by counting all co-occurrences of triplet combinations, for example, J, K, and L. So then we get a marginal PMF estimate, let's call it X, J, K, L hat, that can be approximated by our model of order 3, of course, as in equation 9. And we obtain the full joint PMF by solving a least squares coupled tensor factorization problem using the alternating optimization based on alternating directions method of multipliers, as proposed in reference 1 by Nikos and his co-workers. And they use the, as I said, the least squares criterion to fit this. And this would be the cost function, where here we have our third order subtensor of empirical estimates, and there we try to fit our third order CPD to fit it the empirical estimates, right? It's the least squares cost function, and of course subject to our probability simplex constraints. Yes?
Is the number 3 inherent, or theoretically you could have stopped at 4 or 2 and just
Yeah,
have a
sure.
trade-off
Yes, 4 would be possible, and some people also use 2. Yes, but Nikos didn't consider 2 in this paper, but he looked at 3. But in some follow-up work, people, Xiao Fu actually, I think he used 2 with his students. Xiao Fu, he's the third author here. Okay, the least squares criterion, of course, offers a relatively convenient optimization procedure, but however, it does not provide proper weighting. That means it may attribute 0 probability to an element of the estimated PMF tensor, even when the empirical probability is non-zero. And this is, of course, not so good. Therefore, we chose the Kullbach-Leibler divergence as a more suitable criterion in the context of PMF estimation in reference 2. This is the EU SIPCO paper. Since it treats smaller empirical probabilities in different ways than larger ones. And it forbids a solution that attributes 0 probability to an element of the estimated PMF when the empirical probabilities is non-zero, so when it has occurred, basically. So now the Kullbach-Leibler divergence between 2 PMFs, let's call them X and Y, is defined like this. So this would be the definition of the Kullbach-Leibler divergence. It's of course always greater or equal than 0. And here we express them in terms of the PMF elements, the elements of the PMF tensors. Then we can, of course, expand this expression, and we get equality if and only if X is equal to Y. If X is fixed, so X corresponds, for example, to our empirical estimate, minimizing 11 with respect to Y amounts to minimizing this expression here. C would just be a constant, and here we basically have the sum over this value of X log Y, and the log of a probability is, of course, less or equal than 0. So we can write it, we can just add the L1 norm of the element-wise product, Schur-Hadamard product, between X and log Y tensor here, right? And this is really a convenient expression for the KLD that we use in the sequel. So thus, the following KLD-based coupled tensor factorization problem is posed. Here again, we have now the different cost function, otherwise it's the same. So here we have the KLD between our third order subtensor, the empirical estimates, and this would be the third order CPD that we want to fit to the empirical estimate, of course, subject to our probability simplex constraints. And in reference 2, we have rewritten the non-convex problem as 2 convex subproblems and solved them using reparameterization techniques. And we've also shown that the KLD criterion outperforms the least squares criterion with respect to estimating the true PMF. And Joseph will show this in the simulations later on as well.
That's just maximum likelihood, right?
Not yet. No, it's not maximum.
Minimizing KLD, maximizing likelihood isn't the same?
No, not before you maximum likelihood. We'll talk about that when you directly use the data. That would be maximum likelihood, but you're right. But here we estimate the third order marginals first. In this case. So here you have the estimated third order marginals, right? But you're right, KLD criterion corresponds to maximum likelihood, and I'll mention this in a second. Okay. Any more questions, comments? But this was good, of course. Now we don't want to estimate the third order marginals first. Use the data directly, and this corresponds to maximum likelihood if we use the KLD criterion. So this is exactly what Ami said. Using the observed data, the maximum likelihood estimate of the joint PMF tensor can be obtained, as we have also shown in reference 3, which is of course more efficient because we don't have to compute the marginals first. And in the large sample limit, maximum likelihood, of course, corresponds to the minimization of the KLD between the observed data and the parameterized model distribution. So consider a discrete random vector again, x, n-dimensional, where each xn takes values from 1 to in. And let now y, it's also an n-dimensional random vector, be obtained as a partial observation of x, such that, and this is now, we assume that it's independently for each n, yn is equal to xn with probability 1 minus p and 0 with probability p. So p corresponds to our outage probability, right? And we vary the outage probability later on in the simulations as well. So then the goal is to estimate, so not everybody views all movies and rates all movies, right? This is the outage probability that models this fact. So the goal is now to estimate the joint PMF tensor X from capital T IID observations of Y, of the random vector Y, with outage. So let small y be a realization of capital Y, and B now is the number of non-zero elements in Y. So B variables are basically observed with indices n1 through nb. Then the probability that Y occurs, so n minus b variables are not observed actually. And then we want to express the joint probability of the observed random variables in terms of the CPD, which we can easily do here. And this is just a constant Q. And again, of the product can be written like this. And the factors corresponding to 0 unobserved elements are, of course, marginalized out here in this expression, as before. So let's look at an example. Let's assume we have 4 random variables, and this is our vector y. So the third random variable is not observed because we have a 0 here. So b is equal to 3. And this is the probability that y occurs. And yeah, we can write it as the, and we can marginalize out now sum over all possible occurrences of the third random variable I3, right? And then express it in terms of the CPD. And then, of course, the factor matrix that corresponds to the third random variable is also marginalized out due to the probability simplex constraints. And then here we have order 3 CPD. Okay, the log likelihood of y is given by this expression, the logarithm of this probability, where c is just a constant. And for t IID observations now, y1 through yt, the joint log likelihood is, by ignoring constants, we get this expression here, right? So we have the product over the entries of the observed factor matrices here, weighted by the corresponding values of the loading vector. So this is our cost function directly in terms of the observations, without the estimation of lower order marginals. And we sum, of course, over, we have it this here, T observations, capital T observations here. Then this is the T. Okay, the optimization, this is the optimization problem for the maximum likelihood estimation of our capital N factor matrices and the loading vector. We basically, this is the maximization of the log likelihood, corresponds, of course, to the minimization of this negative log likelihood, subject to our probability simplex constraints. Okay, in reference 2, we have developed a KLD-based alternating direction minimization technique, where we rewrite the non-convex problem as 2 convex subproblems. That is, we minimize with respect to lambda and to each an separately, and then solve these tasks using reparameterization techniques. And now we also came up with an EM-based algorithm. So this would be the, as an alternative, we also developed this expectation-maximization approach. And this arises due to the naive Bayes model that's implied by the low-rank assumption. So let's define the complete data, z of t, as our observations, y of t, and the random variable s of t, which is the unknown latent state. So it takes values in 1 through r. And in the E step, we denote lambda and all ans at the first iteration as theta prime. This is a vector. and then we compute this function, which is the expected value of, this is the augmented data, Z1 through ZT, given our observations and our previous estimates, theta prime. And it actually takes this form. We just use these abbreviations here to write it explicitly. And then in the M step, we can actually maximize it, right, and find closed form solutions. These are updates now, for the elements of our loading vector and the elements of the factor matrices. And then, of course, we have to iterate in the EM algorithm. Okay. We also came up with in the original proposal, actually, we had a hybrid alternating directions EM approach, where we first find an optimal solution to inner convex problems, which is computationally expensive, and then in EM, which is computationally much cheaper because we have these closed form updates that we saw on the previous slide, but it may converge slowly. And Joseph is going to solve both issues, actually, in his part. And in reference 3, we propose this hybrid ADEM algorithm, where we first run a few expensive AD iterations to get to the vicinity of the global optimum, and then switch to the computationally much cheaper EM for refinement. And this hybrid ADEM algorithm obtains much more accurate PMF estimates than the original AO-ADMM algorithm based on the least squares criterion and on triplets. Okay. And in the simulation results that Joseph is going to show, he will also answer the following questions. So more insight into the hybrid ADEM algorithm is needed. Therefore, he will answer the following questions. When exactly do we switch from AD to EM? Is it sufficient to run EM alone? How can we accelerate EM convergence? How do the algorithms perform on real data? And then he will also show extensive simulations that have been carried out in 2 approaches, synthetic data experiments as well as real data experiments for movie recommendations. So now, any questions before Joseph starts? Yes? Yes?
So the assumption that the missing data is independent of the PMF is a little strange.
That's true.
If I like comics, I might see more comics movie and have more missing data in the action.
That's a good point. Yeah, but that's difficult to model. It's difficult to model, right? Yeah. We also thought about this. Yes. We actually discussed it in Tel Aviv. Yes, that's a good point. Yes, Ami?
There's this sort of parallel line of literature in the machine learning world about latent factor models, topic models, Sham Kakaday's work.
Of course, yeah.
Can you explain what is the difference between these two, sort of, in broad terms?
That's a very good point, because of course the machine learning is also used for recommender systems and similar applications, but usually for machine learning you only have one output, right? Only your recommendation, and you don't get the full PMF. If you have the full PMF, you couldn't do anything, and you have much more insight. You can say why do you also get your the hidden random variable, right? So you can use that to classify your users. For example, these are the sick users, these are the healthy users. So you get much more information. If you use machine learning, you basically have a black box and just get the output. But we know why we get this output. So it's kind of...
in terms of the algorithms, is there a crosstalk between these 2 lines of research?
What?
In terms of the algorithms that you used.
Yes?
So EM algorithm for factor models have existed for more than 20 years.
Yeah, but not for this application. Not to calculate the PDF. The CPD, sorry, to the CPD.
But they also use tensor models, right? I think Hasso does, right?
Yeah, but they're not calculating the PMF, sorry, the probability mass tensor. So because they're only looking at basically their recommendation. They're only looking at the final output, right? And they don't. It's not explainable why they get. It's not explainable AI. They cannot really say why they get this result, but we can because we have the whole PMF tensor. But I think in the simulations you also compared it to machine learning, right? Some deep neural networks. Not yet, but we're going to do that. And you need the microphone. Any more comments? Yeah. So you. Oops.
Okay, so thank you very much for that introduction of the background. And so now I'll present some simulation results. Yeah, so first we'll look at synthetic data experiments where we know the ground truth. Yeah. So first we are going to look at the comparison between the least squares criterion and the KLD criterion. So that's the ADEM, as in hybrid algorithm. And then we will compare ADEM and EM, so where we have the hybrid approach and EM alone. And then, so here we will look at the convergence of the log likelihood for both of them. And we will also look at a variety of scenarios. So for example, if we vary the number of observations, if we change how much of the data is missing, and also, as in if we try some different initialization strategies. So the experimental setup is we have 5 random variables. Each of them take 10 states. So our PMF tensor is of size 10 by 10 by 10 by 10 by 10. So it's a 5-way tensor. And we draw the ground truth CPD components. So those are the factor matrices and the loading vectors from a uniform distribution, and we normalize them. And then the observed data has outage probability, P. And then we initialize the factor matrices and the loading vector randomly and normalize, and we average the results of 100 trials. So, and the performance metrics that we use is the mean square relative error between the true PMF tensor and the one that we estimate, and the KLD between the true and the estimated, and the factor match score. So this is a score which compares how well the factor matrices and the loading vector are estimated, and this was proposed in reference 4 by Chege and Calder. So if we look at the least squares criterion versus the KLD criterion, on the left we have the mean square relative error against the number of observations, and yes?
What's the R? Is it constant along the experiment?
R? Yes. So here?
Yeah. What was the chosen range?
So in equation 26, R is the number of components, the number of CPD components. Yeah. Or you could think of it also as the rank of the.
What was in the simulation?
In the simulation. Yes, it was. We used the ground truth rank of 5. Yes, it was 5. It was not indicated here, but the ground truth rank was 5. Yes. Yes. Yeah. So the ground truth was 5, and so here, if you look at the mean square relative error against T, we can see that the. So let me explain about the thoracal maximum likelihood. So this one is it provides a lower bound, and here we assume that we know the true latent state. Yeah, so if we assume that we know the true latent states, we can compute the mean square relative error, and that provides a lower bound. And so if we look at the triplets and the ADEM, we see that the ADEM performs better.
But in fact, of course, you don't know if you have to estimate like this.
Yes. And also in terms of the KLD as well, we see the same result there. Also in terms of the FMS, if we have a factor match score of 1, that means that we have a perfect estimate between the original and the true CPD components. So again, here we see that the ADEM which uses the KLD criterion, performs better than the triplets-based approach. So in the next part here, we look at the convergence of the negative log likelihood. And then, so on the plot on the left, we have so we have, as in different curves, where we run a few initial AD iterations, and then we switch to the EM algorithm. And the point where we switch is shown with the red dot there. And the blue curve here, where we have AD iterations equal to 0, this corresponds to the case where we use only the EM alone. And then on the right, we plot, like it's the same curve as we have on the left, but we plot only the parts of the curves from the red, as in from the red dots. Yeah, so only as a function of the number of EM iterations. So here we see that if we use EM alone, we still achieve convergence. Yeah, if we look at both of these curves, and this is desirable because EM is much more computationally cheap as compared to ADEM. Okay, and so we also looked at the same thing when we vary the outage probability, and we look at the MSRE and the KLD. Again, we see that if we have EM alone, we still have a similar performance, and also in terms of the KLD. Also in terms of the FMS as well, if we run EM alone, this is sufficient. Here we have also some more results where we vary the number of observations, and we also come to the same conclusion in terms of the MSRE, the KLD, and the factor match score as well. Okay, so now next I'll talk about how we can speed up the convergence of the EM algorithm using an algorithm called SQUAREM. So EM is known to exhibit linear convergence, and the convergence of EM is dependent also on how much observations are missing. So the more, as in data is missing, the slower it converges. And so the SQUAREM algorithm is proposed in reference 5 by Varadhan and Roland. It applies a squaring technique, which is proposed in reference 6, that is used to accelerate the convergence of the well-known steepest descent method that for solving a system of linear equations. And the main idea here is that the EM iteration steps can be approximated by a linear equation. And so in this case, the squaring technique can also be applied to EM to speed up its convergence. And then in our case, we adapt the SQUAREM algorithm to the context of PMF estimation, and we have SQUAREM-PMF. So let's look at a few of the ideas behind SQUAREM. So if we, I hope this is visible, but if we start with this well-known quadratic minimization problem, if we take the gradient of this, we end up with this kind of a linear equation, Qx is equal to b. And on the EM side, we can represent each EM iteration as a mapping from a parameter vector theta k, and then we apply the EM mapping f, and then we get the updated parameter vector. And then when the EM algorithm, when it converges, we have what is called the EM fixed point. So this is the point at which applying the EM again does not change the solution. So if we take a Taylor expansion about the EM fixed point, we have this linear equation, yeah, where J here is the Jacobian matrix at the EM fixed point. And then next we can come up with iterative methods to solve the linear equations. So for the qx is equal to b, the well-known one, we have the steepest descent that has this update equation, where the mu k here is the step size. And we can do also a similar thing for the EM algorithm by defining a residual vector r of k, which is the difference between the theta k plus 1, yeah, which is this one, and the current one, or the previous one. And then we have this kind of update equation, and alpha k here is the step size in this case. And then these two update equations can be rewritten as error equations. So we have this form for the steepest descent, and this for the EM algorithm, where we, we define the error as the difference between the current estimate and the optimal one. And then now, how do we accelerate the steepest descent? We use this squaring technique, which is called the CBB method, that was proposed in reference 6 that I showed before. And here, if you derive the update equation and the error equation, if we compare the two of these here, we see that we have a kind of a squaring. And then we say that since EM can also be approximated by a linear equation, we can apply the same as in technique by analogy and end up with the error equation for square EM and the update equation. And so if we look at the update equation, we have our step size here, alpha k. And actually, in our case for PMF estimation, this update equation is what we need to modify so that we ensure that what we get at the end fulfills the probability simplex constraints. So how do we adapt square EM? Yeah, so the original square EM algorithm, it modifies the step size alpha to ensure that the negative log likelihood always decreases. And so but for our PMF estimation problem, we should also additionally fulfill the simplex constraints. And so we adapt the refinement procedure that was proposed to ensure that, these two conditions are met, that the EM stability is preserved, and we also fulfill this probability simplex constraints. So let's go through how what we proposed to adapt the square EM step size. So the parts that are shaded blue here, these are the steps that we proposed, while the ones that are not shaded, these were there in the original square EM algorithm. So what happens in the original algorithm is that once we have the update of the parameter vector theta k at the kth iteration, we compute the negative log likelihood, and then we check whether it is greater than the previous one. If it is, then we reduce alpha by backtracking in this way, and then update again, and we repeat this process until it is less than, until the current negative log likelihood is less than the previous one. So all this is okay, but in our case, we also need to ensure that all the elements are non-negative. So we propose to do the following. So in step 5, we update the parameter vector, theta k, and then if we look at this equation, it is a quadratic equation in alpha in the step size. So the simple approach that we propose is that if there's some elements in the parameter vector that are negative, we solve the equation for all elements of theta k. Yeah. Oh yes, we set 5 to 0, and then we solve it. And yeah, so here we want to find the step size that ensures non-negativity. And maybe to understand this better, we can look at these diagrams here. So for example, we could have a case where we have this quadratic curve for the parameter vector. So as in this is a vector as a function of alpha. And then in this case, the part that's shaded green, this is a part that would be allowed, or these are the step sizes that would be allowed, and the red ones would not be because they would result in negative elements. And the same thing, if you have this kind of a curve, it would be the parts shaded green that are allowed. And then if you have a parameter vector that is that let's say has 2 dimensions or 2 elements, then you have the 2 curves here, and then what you need to do is to search along the alpha axis and find all the segments that are allowed. Yeah, so like in this case, it would be this green one and this one. And then, how do we select the final step size? So what we do is that we pick the segment edge that is closest to the alpha k that was unmodified. Yeah, so that's what we do here. And then we do this only, we use this step size only if it is larger than the original one, so as to avoid a lot of likelihood calculations as in later on. If this is not the case, then we just use the unmodified one, and we project onto the simplex using an algorithm such as 8. And at this point, you may be wondering, okay, so if we have an algorithm to do this, why do we need to go through as in all these steps of searching for the step size? And actually, we ran some simulations where we only did the projection without selecting the step size, and this really had a bad effect on the runtime of the EM algorithm. So I would admit that there is still a question here as to how the step size is related to the likelihood later on. Okay, and now this is a summary of the SQUAREM-PMF algorithm. So yeah, you construct the parameter vector by stacking all factor matrices and the loading vector, and then we run 2 EM updates so that we have theta 1 and theta 2. And then in steps 5 and 6, a 2-point linear approximation of the EM fixed point is computed. And then in step 7, we have the optimal alpha k, or let's say the unmodified alpha k. And then in our case, if necessary, we modify alpha k using the proposed adaptation procedure. We run the final EM update here, and then check for convergence. So, so here you can see that the SQUAREM-PMF algorithm actually it consists of 3 EM updates within it. So, of course, in the simulations, you have to take that into account in terms of how many iterations you allow SQUAREM and EM to run. So let's look at some synthetic simulation results. So here we compare SQUAREM-PMF with EM, ADEM from reference 3, and AOADMM, which is from the original reference. And then we have here we run, for ADEM, we have 20 iterations. And yeah, we have some other parameters here. The model size is also the same as we had before, so we have five random variables and a true rank of 5, and an outage of 0.25, and 10 to the power 5 observations. And the metrics that we use here are the mean squared error between the current parameter vector and the true one, and the negative log likelihood minus the overall minimum across all the 4 algorithms that we are looking at, and also the CCDF of the runtime and the number of iterations. So if we look at the mean squared error as a function of the number of SQUAREM-PMF iterations, So here I'd like to point out that for EM and for ADEM, we, of course, scale the plots so that we have the required number of points to plot. But of course,
the square EM iteration takes 3 EM iterations, right? And this is taken into account, of course.
yeah, here. So we allowed EM to run 3 times the number of iterations that square EM was allowed. And so here, if we look at the mean squared error, we see that square EM actually converges faster and achieves a similar solution to EM. And actually, ADEM in this case achieved a slightly worse performance. So this is another result that shows that if we run EM alone, this is also sufficient. And also, if we look at the negative log likelihood convergence, we see that SQUAREM-PMF maintains the stability of the EM algorithm. So it decreases monotonically for all trials.
You should point out the dash curve as well.
Okay. So for AOADMM, yes. So this is the original one that is based on the triplets. And so in this case, actually we can see that for the if I just go back a bit, we allowed 10 to the power 3 AO iterations and 10 to the power 5 ADMM iterations. But still for this experiment, we did not achieve convergence for AO ADMM. And so, yes. And so in the next result here, we did not consider AO ADMM when we looked at the runtime and the number of iterations here. So, so here we have SQUAREM-PMF, EM, and ADEM. This shows the distribution of the runtime and the number of iterations. So here again we can see clearly the improved convergence of SQUAREM, PMF.
And the lines, they are the mean values.
Yes, these are the mean values, which we can see also in the table here. So if we look at the numerical values, we can see that SQUAREM-PMF runs approximately 3.6 times faster than EM. And if we look at the number of iterations, they're also much fewer. There's also this convergence success rate. So this is a measure that tells us out of the 1,000 trials that we ran, in how many of them did these algorithms converge as opposed to executing the maximum number of iterations allowed. And so we can see that for SQUAREM, it converged on all of them. And this was not the case for the other 2 algorithms. Okay, so now we can look at the real data experiments. So as was mentioned before, we used the movie lens data set, and where we had a data set that had 20 million movie ratings on a half-star scale from 0.5 to 5. We selected 10 of the top-rated ones from action, animation, and comedy, mapped them to the scale of 1 to 10. And this is an example of such a user movie rating matrix, where we have a lot of missing observations or ratings. And then here we describe the training, validation, and testing approach. So we ran 20 independent trials. We shuffled the users. I'm sure you're all familiar with this process of training, validation, and testing. But in the training stage, that's where we learn the PMF. And then we validate by, like for example, we do not know the ground truth rank in a real-world scenario, or at least in this movie case. So we have to test a few ranks, and then we pick the best one that minimizes the loss, or that minimizes the prediction error. And then after validation, we retrain by using the combined training validation data set, re-estimate, and then we test. And for the prediction, we use the MMSE estimate that was introduced before, and the maximum a posteriori estimate. And the metrics are RMSE between the true and estimated ratings, and the mean absolute error as well. So if we look at the results here, so we have AOADMM, EM, and SQUARE-EM. For those ones, we use both the MMSE and the MAP approaches to predict, and we also have some naive baselines here, where we find the global average of the ratings, the user and the movie averages, and a random guess. So if we look at the results specifically for EM and SQUARE-EM, we can see that we have a similar performance, but SQUARE-EM converges much faster than EM, and also we have a better performance than AOADMM. Yeah. So in conclusion, we have presented a maximum likelihood estimation of a low-rank PMF tensor from partial observations. We have shown that the KLD criterion is superior to the least squares criterion in the context of PMF estimation. We have also shown that if we run only EM, as in this is sufficient, and this is desirable because AD is computationally expensive. And then we have also shown how we can improve the convergence rate of the EM algorithm and still preserve the stability of EM using SQUARE-EM-PMF. We have also tested both EM and SQUARE-EM-PMF on real data and found that SQUARE-EM outperforms AOADMM and performs comparably to EM but converges faster. Yeah, so thank you very much for your attention. We can answer any questions.
Any questions?
Yes.
Is it possible to use your method with much greater than 10?
Of course, yeah.
Yes, yes.
The answer is yes. Up to 12, no. More.
Yeah.
But we're also using, we're also looking at models where it's even going much faster than for this naive Bayes model.